Okay, let's look at another AR2. This time we're checking out this AR2, but we're going to go through the same process to try to see if it's stationary by looking at the characteristic equation. So in order to do that, we're first going to put it into backshift notation just for good practice. So, and because we need it in backshift notation, so this will be 1 minus 1.2b plus 0.94b squared xt equals at. Great. All the information about the lags is contained between the parentheses now, and we're going to go ahead and draw our 3 lines just to designate the fact I'm not redrawing this equation. I'm not rewriting this equation. I'm just taking what's between the parentheses because that's the information I need in making the characteristic polynomial. 1 minus 0.2z plus 0.94z squared, because those are operators and these are now variables that I'm going to make the characteristic polynomial, which is degree 2 polynomial in this case, set it equal to 0, and I have a characteristic equation. Great, so this is a degree 2 polynomial, and I would try to factor it. And I'll just we'll have software that will help us factor these, but I'll go ahead and tell you this is irreducible. You could try forever, and you would not be able to reduce this into 2 degree 1 polynomials. So it's irreducible, but it still has roots. Even if we had 2 real roots, we could still use the quadratic equation. So let's write the quadratic equation right here. That is, the root is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. But what the heck are the a, b's, and c's? Remember that this is from ax squared plus bx plus c equals 0, where a is the coefficient of the squared term, b is the coefficient of the to the first term, and c is the constant. So this is written backwards here, right? That's c, that's b, and that's a. But let's go ahead and write those down for good measure. So we'll have a here. I always like to do this just to keep all the bookkeeping straight. So that's a, b is equal to negative 1.2, and c is equal to 1. And most of the time, if not all the time that we'll be doing this, it's nice because c will always be 1 because we're always going to start with xt. So, okay, so we've got that. So now we're trying to find the roots to see if they are outside the unit circle, if they're bigger than 1 in absolute value. So we'll see what that means here in this case, because we'll see quickly that we won't have real roots in this case. We'll have complex roots. So in this case, we've got r, the root, which will actually have 2 here, I'll represent 2 roots, is equal to negative b, so that's 1.2 negative b, plus or minus the square root of b squared, so that's negative 1.2 squared, just to be official about it, minus 4ac, so that's 0.94, and c is 1, and all of that divided by 2 times 0.94. Have to reduce that. And so this is equal to 1.2 plus or minus the square root of, and you can do the math on that, but that turns out to be, if you do this math, negative 2.32. So that ends up being negative 2.32. We end up taking the square root of a negative number, which does not have a real answer. And then 2 times 0.94 is 1.88. So conserving real estate here, we'll note that this is equal to 1.2 plus or minus. Now this is the same as the square root of negative 1 times the square root of 2.32, just to break it down, where we'll note divided by 1.88, where we'll note that the square root of negative 1, the square root of negative 1 is an imaginary number. We represent that as I. So I think we can continue over here. We'll say that that's equal to 1.2 plus or minus I times the square root of 2.32 divided by 1.88. So that 1.2 will get divided by 1.88. That square root of 2.32 will get divided by 1.88. And we'll end up with the roots being 6.38 approximately, 6.38. That's 1.2 divided by 1.88, plus or minus, and this will be 0.810, and so I just put that first, and we'll put the I at the end. And so that's it. We've got two roots here, right? We've got a degree 2 polynomial, we've got two roots, and these are complex roots because they have the imaginary I in it. And complex roots always come in pairs. It's 0.638 plus 0.810i, and the other root is 0.638 minus 0.810i. Now, great, we've got the roots of the characteristic equation. The next question is, of course, are they bigger than 1 in absolute value? And it's tough to say. It's got a real part, which is certainly less than 1, and it's got an imaginary part, that 0.810. And so again, it's tough to tell. So it turns out though that what we're really asking is how far away is this root from the origin? And right, that's really what the absolute value of a real number, like if you had 1.11, how far is that away from 0? It's 1.11. Negative 1.25, how far is that away from 0? It's 1.25 units away. It's absolute value. But that's when we have real numbers, it's very easy to see how far they are away from the origin, away from 0. But right now, we've got the complex plane where this number line is the number line we've always lived in since we were little kids studying mathematics. That's the number line. But there's also an imaginary axis, and that's this y-axis here. So we'll put an I up there for imaginary. And so now we see that's 0.638. Let's call this 1. Let's just cut to the chase. That's 1 and negative 1, where we said, hey, if we had our real roots over here or over here, that was indicative of stationary behavior. And any root inside here or inside here was indicative of non-stationary. Or if it was on the negative 1 or on the 1, if it was exactly 1 away from the origin, we said that was non-stationary. But now we've got so that's 0.5 there. So this is about 0.638. That's the real part. And then if we have a 1 up here, say, and we have a negative 1 down here, that represents the imaginary part, at which this one is about at, right up here at, say, 0.810. Then I'm going to be really terrible and probably draw a football, but the idea is that if we draw a circle, not too bad, that represents the radius of this circle is 1. So anything outside that circle will be more than 1 away from the origin. Anything on the circle will be exactly 1 away from the origin. And anything inside the circle will be less than 1 away from the origin. And where are we? We are at negative 0.638. We are right here. And so graphically, you can see it. This one's going to be stationary, but let's go ahead and prove it. This is the distance. This is from the origin, represented by that line there. And note that we can, I am going to, that is, sorry, excuse for a triangle, but note that that represents a triangle. That is a little better. Okay, and so what is the leg, right? This is just a right triangle. Trying to find that distance. Clearly that distance is bigger than 1, but let's go ahead and show it. So this distance here is just 0.810. So that distance here is 0.810. From here to here is 0.810. From here to here is 0.638. So long story short, this here from the Pythagorean theorem is just, we can put this here, that this is just the square root of 0.638 squared. Again, the Pythagorean theorem, this leg squared plus this leg squared equals this leg squared. So this leg is the square root of the sum of these two legs squared. And that's that. And if you do that, that's going to equal, I've already done it, about 1.31. No, that is going to equal approximately 1.031. 1.031, which is just outside the unit circle. Nothing really to compare it to here, but that's relatively close to the unit circle. And so our final thing to do would be, well, how much is that behavior going to be expressed? And so this, the absolute reciprocal of this, we'll go ahead and talk about the absolute reciprocal. So we'll say the root, what we'll actually do is call this the modulus. So the modulus of R here is equal to, it looks like absolute value, but when we're talking about complex numbers, That's known as the modulus. And it just represents the distance that point is away from 0. And so the modulus, we just said, is 1.031. The modulus equals the square root of one leg squared plus the other leg squared, or the real part squared plus the imaginary part squared, or the absolute reciprocal. Absolute recip is 1 over 1.031, which equals approximately 0.9605. Right? And for stationary models, we know that this is stationary. That's outside the unit circle. It's more than 1 away from the origin. We take the absolute reciprocal, which must be between 0 and 1, and we don't have anything to compare it to, but that's pretty close to 1. It's the biggest it can get is to be 1 for a stationary model. So we'll talk more about the behavior associated with complex roots, right? It doesn't wander or oscillate. It actually has frequency. It actually have periodic behavior, but this would be representative of how strong that type of behavior is expressed in this particular process. So once again, we had an AR2 here. We put it in backshift notation. We found the characteristic polynomial. It was degree 2, of course, because it was an AR2. We set it equal to 0 to get the characteristic equation. We couldn't factor it into 2 degree 1s, so we used the quadratic equation to come up with its roots, and it yielded us complex conjugate roots. We then took that and figured out how far away. We looked at the modulus of those roots. That happened to be the 0.638 plus 0.810. The 0.638 minus 0.810 would end up down here, so I'll let you think about that. But it will have the same modulus. Absolute reciprocal of that modulus is 0.9605. And and this is definitely a stationary process. So lots more to talk about. We've introduced a lot of concepts here, but great work. I'll see you in the next one.